In this session, I want to prove that if y equals to x to the power of n, then dy dx is equal to n times x to the power of n minus 1. The formula for differentiating a power of x. Now in this proof, I shall only do it for n an integer. Okay, so n is an integer which is more than or equal to 0. Now later on I'll sketch out a proof for the case where n is a fraction. And in a separate session I shall talk about how it could be done when n is negative. The method I shall use is called the method of induction. This is how it works. It is done in 3 steps. Step 1, I shall prove it. It meaning the statement that I wanted to prove. So it is this. So I shall prove it for the starting value of n equal to 0. Alright, that's the starting value of n. Then I shall assume that it is true for n equal to a certain number. Okay, then I shall prove it for the next number. That means for n equals to k plus 1. And in step 3, I shall look back at these 2 results and say that since if n is true for a particular number, then it must be true for the next number. And since I've proven it for the starting number where n is equal to 0, therefore the step 2 shows that since I know that n equal to 0, it is true for n equal to 0. Step 2 shows that it must be true for the next number, which is n equals to 1. Alright, so since we know from step 1 that it is true for n equal to 0, then step 2 tells us that it must be true for the next number. So it is also true for n equals to 1. And since it's true for n equals to 1, step 2 tells us that it must be true for the next number, which is n equals to 2. So it will be true for n equals to 2, and then again step 2 tells us that it's true for the next number, which is n equals to 3, and we can just go on forever. Alright, and because of this connection between 1 and 2, we can say, alright, since we understand this now, we can say that therefore it means the formula that we wanted to prove. Therefore it is true for all n. Right, for all n that we are interested in this case, meaning integer n that is more than or equal to 0. So this is the plan. Let's start with the first task. Prove it for n equals to 0. If we look back at what we want to prove, when n is equal to 0, I have x to the power of 0, which is 1. And I have 0 there, which makes this 0. So let me write this out with n equals to 0. Okay, that's the step 1. I want to prove that if y is equal to 1, dy dx is equal to 0. There are two ways we can do this. The quick way is to say we can either say since dy dx is the gradient of a graph, and since the graph for y equals to 1 is a horizontal line going through 1, therefore the gradient of this is 0. Therefore dy dx is 0. And that proves the point. Or I can do it more rigorously using the definition of dy dx. Dy dx is the limit as delta x tends to 0 of delta y by delta x. And delta x means that if I go to a particular point on the x-axis, and there's a corresponding point on the graph. And if I think of increasing x by a small amount, which I call delta x, then my new point would be there. So that's delta x. It's a small interval there. Delta y would then be the increase in y from that point to that point. The increase in the y value. But since this is a horizontal line, y stayed the same. That means y has not increased, and therefore delta y is 0. So I have delta 0 over delta x. And And 0 over delta x is 0, whatever delta x is. So therefore, the answer is 0. Alright, it's already 0 before I let delta x go to 0. So when I then let delta x go to 0, it makes no difference, still 0. So that's my more rigorous way to prove this. So in either case, I have proven this statement for the case where n, this is the case where n is equal to 0. Next, we assume that the formula is true for n equals to k, and then prove it for n equals to k plus 1. Let me then write out these statements. Step 2. We assume that if y equals to x to the power of k, then dy dx equals to kx k minus 1. So this is what we assume. And we want to prove that if y equals to x k plus 1, then dy dx is equal to k plus 1 x to the power of k. Alright, this follows from using this formula that we want to prove. We want to prove that this is true when n is k plus 1, then this becomes k plus 1 and that becomes k plus 1 minus 1, which is k. The way to do it is now to pretend that this is true, because we are supposed to assume that, and make use of this to prove this. Okay. Now let me write this out using the definition of dy dx. This one. This is right when I'm doing this for what I want to prove, which is when y is equal to x k plus 1. Alright, then the definition of dy dx is the limit as delta x tends to 0 of delta y over delta x okay. Now I want to substitute this function for y into here. Draw a long line for what I want to substitute. The delta y is the change in this function when x is increased by delta x. So before x is increased, y is just x to the power of k plus 1. After increasing x by delta x, x here becomes x plus delta x. So the function becomes this to the power of k plus 1. Therefore, y is this at first, and then after x increase, y becomes this. Therefore, the increase in y, delta y, would be the difference. Let's carry on from here. Carry on with rearranging the dy dx for this. I shall try to make use of this formula, this one, in some way down here. Now, to get an idea of where we are heading, alright, if you like to get some inspiration rather than, trying to rearrange this blindly, it helps to think about this. Think about how this might be connected to this. Now here, if you look at this expression, there is a limit, there's a delta x goes to 0, meaning that this expression comes from the definition of dy dx, this one. So this suggests that we should perhaps also look at the definition of this. So let me do that. For the case where this time I'm going to take y to be x to the power of k, that means I'm going to examine, I'm going to look more closely at this assumption and see what the definition looks like, meaning what the expression looks like if I make use of its definition. Okay, if I make use of this definition here for y equals to kx, I would get something which looks pretty much the same, except that in case instead of a power of x plus k, which appears here and here, I have a power of k. So it would look the same as this, but with the powers equal to k instead. Let me write this down. So I expect this to be x plus delta x to the power of k minus x to the power of k over delta x. So this is what we assume, alright? We have assumed that this is true. Okay, so for this part of the proof, we don't worry about this. We just want to make use of this. But it is this that we want to prove. So we don't know whether this is true. We have to find out. And the idea is to somehow make use of this. Now we can now compare this with this. They do look quite similar. Perhaps I might be able to rearrange this until some part of this look or becomes the same as this. Then I would be able to make use of this. So let's try that. And now I'm switching back to y is equal to x plus x to the power of k plus 1. I want to carry on from there and see if I can rearrange that. Y equals to x to the power of k plus 1 dy dx. Now I am going to carry on directly from here. Limit as delta x tends to 0. Let's take a closer look at these two. Okay, that clearly is the more complicated looking part of the whole definition thing. The difference between these two is really just the power of k, just that I have an additional 1 up here. So the simple way to rewrite this so as to relate this to this might be to just write this as two separate factors, and x plus delta x to the power of k times x plus delta x, which is just to the power of 1. So this is the same as that. And if you look at this and this, we now see that this part looks like that. Now it might or might not work, but I think it would, because I've sort of tried it just now. So let's press on. I am just going to copy out the rest of the expression from there to here. So we have this now. Okay. Not too sure what to do next, but we could just look at this and try some rearranging, some simple manipulations we would do in algebra. Like, for example, in this case, I have a bracket x plus delta x multiplied by this thing. So I am going to try and remove this bracket and see where that leads us. The first term is this times x, and the next term is this times delta x. Okay. This is what we have. Doesn't look very illuminating, but let's compare again with what we have. All right, that's always a good place to look for inspiration. It is this thing and this thing here that looks like this part in the assumed formula. So if we look a bit further, in this formula there is also a x to the power of k and delta x. So delta x are obviously the same, no problem with that. But we also have a x to the power of k. And here I have x to the power of k plus 1. They are very similar, except that this has an extra factor of x. Now, taking some lead from what I've done with separating these two out, we could perhaps also do it for this. If I separate out a factor of x, I would get a factor of x to the power of k, which is the same as this. But what would be the point of that? Well, if I separate out a factor of x, notice that we also have a factor of x down here. Okay, then perhaps we could then combine those two, and we might even get something that looks exactly like the two of these together. It's looking a bit more promising now. So I am going to bring those two together. Now I'm going to say that I want to treat that as x to the power of k times x. Alright, so between this and this, there is a common factor of x which I can take out of a bracket. So if this x is this one and this one, then I can make a bracket, and the first term would be this, next term would be that, and there is a minus sign. So I've turned those two terms into this. Now, and this is good because this looks exactly like that. So maybe we are getting somewhere after all. There is this other term here which I shall just copy out, and then the delta x. If I look at this expression now, this term contains a delta x as a factor. If I divide this term by this term, the delta x would cancel. This, as we've seen, looks exactly like that. And there is over delta x here, which I also have here. So to complete this connection, why don't I separate this out to make this part look exactly like that? Right, I have x here times this part. Okay, plus this divided by delta x. Delta x cancels, and I have just that. We can now take the limits when delta x tends to 0, because we know what to do with both of these. For this one, when delta x tends to 0, since this is exactly the same as this, we know what the answer is. Alright, we know what dy dx is when y is equal to x to the power of k. It is what we assumed earlier down here. When y is equal to x plus k, dy dx is equal to this. So therefore this is what we can write down for this limit. I should do that. That would be k x to the power of k minus 1 plus that one. The limit when delta x tends to 0. So that just goes to 0 and I'm left with x to the power of k. Now this is good because it's just a simple, two simple expressions I can simplify. K, x times this gives x to the k plus x to the power of k. So putting these two together, I get k plus 1 x to the power of k. Now, is that not what we set out to prove? We wanted to prove that if y is equal to this, then dy dx is equal to this, which is exactly the same as this. So, we've done it. We have proven that this is true here. So this completes the step 2. Now in the step 3, if we look back at what I've written earlier, using this reasoning, alright, that if steps 1 and 2 are true, then the statements, right, then this statement must be true for all n. We can conclude that since we have proven it, we have indeed proven it for steps 1 and 2, we can just say therefore okay, I'll write this out. Therefore, y equals to x to the power n and dy by dx equals to n x to the power of n minus 1. Okay, let's just cross this out. N x to the power of n minus 1. There. So this is true for all. In this case, we have integer n more than or equal to 0. So this completes the proof. This proof is valid for only for n that is an integer and that is either 0 or positive. But what if n is a fraction, or what if n is negative? Now I shall briefly sketch out a proof for the case where the power is a fraction or negative. It will have to make use of some of the exponential function and logarithms, which properties that I shall prove in a separate session. Okay, so I'm just going to assume some properties about those functions. And this is what I want to prove now. I want to prove that, okay, so this is our next proof. Prove that if y is equal to x to the power r, okay, then dy dx is equal to r times x to the power of r minus 1. Okay, where r is a real number. Alright, real means it can be fractions or it can be negative. It does not have to be integers. Right? And the proof, this is how it goes. We start with y equals to x to the power of r, and we say that we shall take the natural log of y, of both sides. So ln y is equal to, the log of that would be r log x. We can bring down the power. Okay, and we then differentiate both sides with respect to x. Now on the right side, if I differentiate log x, I'll get 1 over x. Again, I shall prove this in a separate session on exponential functions and logarithms. On the left side, I have likewise, similarly, I have 1 over y, but because y is a function of x, I need to then multiply by dy dx. So this makes use of something called the chain rule, which I'll also prove in a different session. Now once we arrive here, we more or less have the answer. We can find dy dx just by rearranging, just by moving y to the other side and then substituting the expression for y. Okay, so in fact, I can just write it out here, the final step. Dy dx is equal to r times 1 over x times y, which I move over here. But y I know is x to the power of r, so times x to the power of r, and I can simplify that to r times x power of r divided by x gives r minus 1, which is what we wanted to prove. So this completes the proof. We'll stop here.